So this is a question that I probably can't put on it in its entirety on your exam, mainly because this is a rather difficult question. I mean, if this mass is being held in place and you are only dealing with this small mass, then great. That's a standard inclined plane problem. I think you have some homework questions. You can do those fine. What makes this problem difficult is when this mass speak, the ramp is allowed to move. And in previous semesters, people had a situation like this in their lecture, and people were more used to this exact setup. That's why it was on their exam. But I'm pretty sure part C and part C might be barely on the edge of being doable, and D is probably, yeah, D is very difficult. So I can tell you that I definitely can't give this as your exam. But what I want you to do was at least to show you the setup, that even when the problem is very difficult to eventually solve for, you can still, it is possible for you to draw the free body diagram and have some sense of what happens in the setup, and I guess also understand why it would be complicated, difficult to solve for. So let me at least do part A and draw a free body diagram. So it as assuming that no other force was applied, draw the free body diagrams for the ramp and the block. So the free body diagram would look like you have the, so let me do this one for the ramp, for the block, and do this one for the ramp. So when you're drawing free body diagrams, I am going to be a kind of a parrot repeating the same thing over and over. I like to draw the forces that, I like to draw only the forces that I have to draw. So on each of these free body diagrams, I know there has to be gravity. There's always gravity. So that's always what I'm starting out from. It also gives me a reason to write down additional forces that are going to be on the object. So speaking of this box on the ramp, once you say that gravity is pulling it directly downward, but it's not accelerating directly downward, then you have to recognize that there's an additional force on this mass. That is the normal force coming from the ramp. So you have to draw that normal force. And I think this part is fairly standard. You have seen this with the inclined plane question. And with the ramp too, once you recognize that there's weight pulling it down, but it's not accelerating directly downward, then you have to recognize that, oh, there's also normal force on the ramp. And I guess this is where I'm hoping you realize that this normal force is not the same as this normal force. And so that I don't make a math mistake later, I'm going to make sure that I use different labels for these two. And I think most people get up to this point, and this is the part that this is the part that makes even part A here a bit of a tricky question that some people might not get everything right. Is you have to remember to do Newton's third law check. So I hope from doing homework questions so far, you are not asking, what is Newton's third law check? That you have to check for the action-reaction force pairs. This is something you always have to worry about whenever you have two objects or more interacting with each other. So what this means is for each one of these forces, you have to do a check of, is it an external force? Then you don't have to worry about it. It's good. You don't need to find the reaction force. It's going to be outside your system. And two, if it's internal force, have you already drawn the reaction force pair somewhere on your free body diagrams? So gravity is kind of easy. Both the gravities here are external forces. It's coming from the Earth. You could draw the reaction force on the Earth, but it doesn't kind of matter. It doesn't change anything. And this second normal force is also an external force. It's coming from the table. I'm not drawing all the forces on the table, so the reaction force is in the table. I don't have to worry about it. But the reason you do this check is so that you realize that this normal force here is not an external force. It is an internal force. So this force, if we call this the action force, I need to have the reaction force to this on the object that exerted that force. This is coming from the ramp. That means the ramp needs to have a reaction force of equal magnitude as N1 and in opposite direction. And I hope once you draw it, then it makes sense that, yeah, of course, that had to be there so that this ramp would get pushed to the left, as you might have intuitively expected it. So this Newton's third law check is what makes even part A a little bit tricky because, I don't know, people forget to do the check. And this requires that you understood Newton's third law correctly and thoroughly. So that's it. This is the correct, complete free body diagram. So it says, when no external force is applied, the block M is allowed to slide down the ramp. The ramp will slide to the left. Right, what I was talking about. So we apply a force on the ramp so that as block M slides down the ramp remains stationary. What is the magnitude and direction of force F? All right. So this normal force is pointing down and left. And I only really, so I mean, one way you could apply this force is to counter this normal force exactly. That's one option. But I think that's harder than it needs to be. Really, the easiest thing to do is to say, well, I'm gonna apply however much horizontal force there needs to be so that net force in the horizontal direction will turn out to be 0. And in the vertical direction, you don't have to actively try to balance it out. Really, this normal force N2 is designed to make all the vertical forces 0, add up to 0. So for part B, this is the tiny little modification to the free body diagram you'd make for part B. And once you've made that, then I think, yeah, I guess it says feel free to use the free body diagram drawn above. Once you've done that, then the rest is a standard strategy question. In fact, this then becomes kind of an exact setup you have seen before. So for this mass, it does become a standard mass on an inclined setup with x and y axis. So x-axis going along the plane, y being perpendicular. I think a lot of people have done the question, so you can do this question, and in the process you will find what N1 is, and you can use that N1 to solve for F there, and then you will be done.